Hello, in this lecture, we are going to continue with our discussions on ordinary differential equations. And we're going to do a few more questions that have been asked in examination, and accordingly, we'll drive the theory. Okay. So as promised by me, in these lectures, we are going to discuss differential equations, the solution of the differential equations, keeping in mind the exam demand. Okay. So this is what I've been thinking all around. And so let us do a few more questions. Okay. So let us start with a few questions first, based on ordinary differential equations. And once you'll be comfortable with the exam things, I think then we'll shift to another topic. Okay. So we were doing ordinary differential equations. Just try to solve this differential equation. The question says, whenever I write WOTF means which of the following curves, gives the solution of the differential equation k1 dx by dt plus k2 x equal to k3, where k1, k2, k3 are all positive constants, all belong to positive real numbers, you can say. Okay, with initial conditions which have been dictated like that is x equal to 0 at t equal to 0. These are the initial conditions given to you. Okay. Now option number A that has been asked, that has been given, is this. Option number 2, and this is like getting asymptotic somewhere. The option number 2, which has been given to you, is this way. Okay. Option number C, which is given to you, is this. And option number D, given to you, is a quadratic sort of, but somehow it is asymptotic. So it's not exactly quadratic, but somewhat resembles. But here it is asymptotic, like it is going and increasing and getting like these are the two vertical asymptotes to this particular function. So this is x versus t, again x versus t, again x versus t, and again x versus t. I hope it is clear. Now, how to go about these questions. So let us try to solve this question. Okay, and this particular question has been asked in GATE exam. Okay. So how to go about it? Let us do. Okay. So how to go about it? So question given to us was k1, then dx by dt, the differential equation, that is k1 dx by dt plus k2x was given as k3, where k1, k2, k3 are positive constants. All these things are given as positive constants. Okay. So what I'll do, I'll simply try to solve it. Dx by dt plus k2 by k1x is equals to k3 upon k1. And like how to solve this differential equation? This is a linear differential equation. So you can find the integrating factor first. So integrating factor would be integral e to the power k2 upon k1 dt. Okay. So the integrating factor would be simply e k2 upon k1 t. Okay. So x as a function of t into integrating factor, which is e to the power k2 upon k1 t, should be equal to integration k3 upon k1, integration of this. So this will become k1 upon k2 e to the power k2 upon k1 or t, and some constant of integration, which I'm right now writing c. Initial conditions are supplied to you. So if I use the initial conditions, so x as a function of t, I will get as k3 upon k2 plus c e की power minus k2 upon k1 times t. Now, what are the initial conditions? Initial condition is that at t equal to 0, your x is equal to 0. So if you replace t equal to 0 here, you'll get x equal to 0, which implies your c is equal to minus of k3 upon k2. I think this is something that you can verify on your own. So this is it. So overall, x as a function of t, you will get as x as a function of t, you will get as k3 upon k2, and if you take the bracket 1 minus e की power minus k2 upon k1 times t. Okay, I hope it is clear. This is the solution which I have got. Okay, now I have to see which of the following graphs satisfy the conditions. Like for example, the graphs are given here above. You can see there are 4 graphs given to you. Now we have to find which of the following graphs correspond to this particular solution. Okay, so I told you on the very first day, whenever you have to make the graph, try to take the derivative, try to see how it behaves. So for example, all the graphs, leaving the last one, all the 3 graphs first, let us check these 3 graphs. Okay, and all the 3 graphs you can see are on the t greater than 0 axis only. So only for t greater than 0, let us make the graph at first. So at t equal to 0, you can clearly see that your x would be 0. That is very much clear. See, at t equal to 0, if you replace 1 minus 1 would become 0. So at t equal to 0, x is 0, which was actually given in the initial conditions as well. So all the 4 graphs are satisfying the same, so you cannot justify anything from here. Now, let us try to take the derivative of it. So once we take the derivative part, so x dash t will be equals to what? It will be equals to k3 divided by k2, and then you take the derivative of exponential. The derivative of exponential, you'll find minus gets absorbed. So e की power minus k2 upon k1 times t. Okay, so this will get cancelled. K3 and k1 are positive. So overall, you know that your x dash t is given by power minus of k2 upon k1 t. And you know that for all t greater than 0, your exponential is a positive function. So I can write that my x dash t would be a positive thing. X dash t being positive thing means x as a function of t is a monotonic function, and I can write more appropriately, it is a strictly increasing function. Is that clear? It is strictly increasing function. So x dash t is given by e की power minus k2 by k1 t, and this is greater than 0, which implies that my the derivative, that is x as a function of t, the derivative of x as a function of t is positive, which implies my x is an increasing function. Is that clear? Now, if I take the second derivative in order to understand the concavity of the same function, so I'll get minus k2 upon k1 e की power minus k2 upon k1 t. Is that clear? Which happens to be negative. So overall, I know that my x is such a function which is increasing but at a decreasing rate. Increasing at a decreasing rate. And if it is increasing at a decreasing rate, okay, so x as a function of t is increasing at a decreasing rate. What does it mean? It means that this cannot be the graph for sure because it is increasing at an increasing rate. Forget about it. This cannot be the graph because it is non-monotonic, because you can see here the graph is increasing, that is, a function is increasing, and then it is decreasing. You can see that your function is entirely increasing for all t greater than 0. Okay, so second cannot be an option. Even third cannot be an option. D cannot be option. Answer should be this. Let us verify. Okay, so in order to verify, let us first take what is the limiting behavior of x as a function of t as t tends to infinite. So as t tends to infinite, your xt would tends to k3 upon k2. This is very much clear that as t tends to infinity, this will go to 0. Overall, your function would tend to k3 upon k2. Okay, so what I can write, I can simply write that my function would be increasing at an increasing rate starting from this particular point. That is at t equal to 0, my x as a function of t would be increasing at a decreasing rate, increasing at a decreasing rate. And as t tends to infinity, it will start saturating and it will start being asymptotic to this particular value, that is k3 upon k2. So the option that is the most feasible one, most appropriate one is your A. Is that clear? So all these questions are quite easy. I hope you might be getting all these things, isn't it? Okay, is that clear to you?
Yes, sir.
Okay, so these are very easy questions as such. So you can do all these questions. A few of them I'll do for you, and then we'll do a few other questions as well. Okay. Uh, so let us focus our attention to second order differential equations first, and then again I'll shift to linear differential equations only, like exact forms and all those things which are less asked in the examination. But still, let us first do second order linear differential equations. Okay. Okay. So consider. I hope you're aware with the solution things. I'll do all those things as well. Don't worry. So consider a second order homogeneous linear differential equation. Second order homogeneous linear differential equations. Okay, so consider a second order homogeneous linear differential equation given by a naught as a function of x y double dash plus a1 as a function of x y dash plus a2, and then you had some as a function of x y equal to 0. Whenever I'll say homogeneous linear differential equation, means on the right hand side you will not have any such f of x here. Okay, where for a naught x is non-zero. For all x belongs to some interval I, which is an interval of existence of the differential equations. The solution for the differential equation would exist in this interval. Okay. Now, here a naught, a1, and a2 are continuous functions of x. These are nothing but these are continuous functions of x. So these are nothing but continuous functions of x. Okay. Now, with this differential equations, there can be two solutions. Let's say solutions are given by y1 and y2. Let y1 and y2 be two solutions of the above ordinary differential equation. I'll write second order homogeneous linear differential equations. Okay. Then, in order to judge that these solutions, that is y1 and y2, are linearly dependent or linearly independent, there is one function, one determinant which we use, which is called as Wronskian determinant. This is called as Wronskian determinant. Okay. Now, what sort of information it will give? It will let us know that if this particular Wronskian determinant is being judged for the linear dependence and independence of the solutions of the second order homogeneous linear differential equation, what we need to see that whether this Wronskian determinant is zero or non-zero. Whether this Wronskian determinant is zero or non-zero. If it is zero, then my solutions y1 and y2 are linearly dependent. And if it is non-zero, then y1 and y2 are linearly independent. Okay, mind you, this is not true for any functions. Okay, as in, मतलब अगर कोई दो functions हैं, and if you want to find that whether one is linearly dependent or another, you will not resort to Wronskian determinant. But for the solutions of the differential equations, one can resort to Wronskian determinant in order to judge whether the solutions are linearly dependent or independent. Now, in general, in very easier way, what you can say that if I'm saying that my function is linearly dependent on another, if I'm saying that y1 and y2 are linearly independent solutions. Okay, so the set of such solutions, I'll write here, the set of such solutions are called as fundamental set. Is called as fundamental set. So whenever I'll say that y1 and y2 form the fundamental set of solutions for the second order homogeneous linear differential equation, it is understood that I'm saying that y1 and y2 are linearly independent. Okay. Now, what I was saying is if I'm saying that y1 and y2 are linearly dependent, it implies y1 can be expressed as some constant times y2, or y2 can be expressed as some constant times y1. If this is the case, I will say that my function is linearly dependent. And if this is not the case, let's say if I say that e to power x and x, are they linearly dependent? So you'll say no, they are not. But if I say that mod x and x, are they linearly dependent on 0 comma infinity, you'll instantly say yes. Let's say this is your function f1, this is your function f2. For all positive number, you know that your modulus of x is given by x. So you'll say that your f1 is 1 times f2. So f1 is equal to f2 means f1 is 1 times f2. So I'll say that my mod x and x are linearly dependent on this interval. In fact, you can write that your mod x and x are linearly dependent on minus infinity comma 0 as well. Say this is your function f1. Let's say this is your function f2. So you can say that f1 is negative of f2. So here also one function can be expressed as constant multiple of another function. So if you can write in this fashion, that is, if you can express one of your function in constant multiple of another function, then those two functions are called as linearly dependent functions. And if you cannot do so, then you will say that my two functions, that is my two of the solutions, are linearly independent. Is that clear? Okay. So let us first mention what is Wronskian in general. So in general, for two, I'm writing it for second order linear differential equations. I'm writing the Wronskian determinant, and the Wronskian determinant for the second order homogeneous linear differential equation. If I write in general, also you can write. Wronskian is not necessary that it has to be homogeneous. You can write it for in general for second order linear differential equation. The Wronskian determinant is given as y1 x, y2 x here. Here you can write y1 dash x, and here you can write y2 dash x. So this is how you can define the Wronskian determinant. So Wronskian determinant will be y1 y2 dash minus y2 y1 dash. Is that clear? Okay. So a few of the properties we are going to discuss for the Wronskian determinant. Most of them are usually not asked in the examination, but I'm just teaching you for the sake that you must remember all these things. So the first property is sometimes referred to as Abel's formula. First property you can say, or you can say Abel's formula. Now what does that do? I'll explain the room for you. So for example, if I want to find that what is my Wronskian at some general point, okay, and if I know that my Wronskian at some known point is x naught, then I can relate these two by this. So if I want to find Wronskian at some point x, and if I know the Wronskian at some some other point, let's say x naught, so I can write my Wronskian as a function of x as Wronskian x naught. This is the Wronskian known at some known point, and this term where a1 and a naught are these. We'll come up to this, don't worry. These are the a naught and a1. Now how to understand that what I have done is, see, I already know that my differential equation was given by a naught y double dash a1 y dash plus a2 y equal to 0. Okay, and the other part was, if I say that y1 and y2 form the solution, so y1 must satisfy this differential equation, and y2 as well must satisfy this differential equation. Is that clear? Now what I'll do, I'll multiply this equation number 1 by y2, and I multiply this equation number 2 by y1. So what will happen if I do so? What I will get? I will simply get a naught y2 y1 double dash minus, sorry, plus a1 y2 y1 dash. This y2 y1 and this y2 y1 will get cancelled. Remaining is minus a naught y2 double dash minus a1 y2 dash equal to 0. And sorry, here I will have y1 as well, and here I will have y1 as well. Okay. Now, if you take these terms like a naught, if you take common, this is y2 y1 double dash minus y2 double dash into y1 plus you can write a1, and then you can have this y2 y1 dash minus y2 dash y1 equal to 0. Is that clear? Now, if you see this particular thing, can you not see that this is negative of Wronskian? So if I write Wronskian as y1, y2 dash minus y2, y1 dash, this was it. If you remember, this was it. Like this was the Wronskian y1, y2 dash minus y2, y1 dash. So if I replace this entire thing, you can see that if I replace this entire thing as minus of Wronskian, is that clear? So if two solutions are y1 and y2, this will be the Wronskian of the two solutions y1 and y2. And if you see it clinically, if you try to find the Wronskian dash, what it will be? It will be y1 dash, y2 dash minus y2 dash, y1 dash plus y1, y2 double dash minus y2, y1 double dash. So this gets cancelled. So you're left with y1, y2 double dash minus y2, y1 double dash. So what is this? If you remember, if you can see that this is again minus a naught. This is Wronskian ka derivative. Is that clear? So I can put all these things in variable separate form. So w dash upon w is equal to a1 upon a naught with a negative sign. Integrate these two things with respect to x, and what you'll find ln w is equals to integration of minus of a1 as a function of x divided by a naught as a function of x dx. And in general, if I know my Wronskian at some known point, so I can integrate it from x, like here would be some constant, and some constant of integration would be there. Let me write it as Wronskian w naught and integrate it from x naught to x. Okay, so integrated from x naught to x, or you can simply write it as k, some constant k, and do the same. And if you take these values, you'll find that Wronskian as a function of x is given as Wronskian at x naught, which is w naught is, I will write that w naught is Wronskian at some known point, exponential minus integration from x naught to x, a1x divided by a naught x dx. Is that clear or is that not clear? There are a few more properties related. Usually I teach them to mathematics students, but I will teach you here as well, so that at least you get a know-how of things. Is that clear or not?
Clear, sir.
Okay, so this is your Wronskian determinant, and Wronskian determinant for your differential equations, that is the solution for the differential equations, in particular linear differential equations, would assert that whether your function is a linearly dependent one or an independent one. Okay, the second property that I like to mention here is the property is that Wronskian is either identically zero or non-zero. Wronskian is either identically zero or non-zero. What does that mean? It means that if by chance, if in any way you know that at some point, that is even at x naught, if you know that your Wronskian is non-zero, then entirely your Wronskian will be non-zero. Entirely means on the entire interval of existence of the solution. Now again, you will be surprised to know why I'm doing this. See here, let us take one of the most fundamental equations, that is the simple harmonic one. So you know from this particular equation that x as a function of theta would be some cosines and sines. Okay, I'm writing some c cos theta plus d sine theta. And for this particular differential equation, the solution, I can write it for all theta belongs to R, isn't it? So what will be the interval of existence of the solution? The interval of existence of the solution would be entire real axis. Is that clear? So interval of existence of solution will be entire real axis. Have I done a mistake somewhere? Nothing. So this will be like m square plus omega square equal to, sorry, my mistake. So there will be some. Okay, is that clear? So overall, understand that for all theta belongs to R, these solutions are different. Is that clear? For all theta belongs to R, For all theta belongs to R, my solutions are defined. So this is called as your interval of existence. So if I know that at some point x naught, my Wronskian is non-zero, then it asserts that Wronskian will be non-zero for all x belongs to I, where I is the interval of existence. Is that clear? And at any point, if you know that your Wronskian is zero, then it is entirely zero. Then you don't have to check for all other points. It will be zero for all x belongs to I. Now let us see how. The answer is very much evident from the Abel's formula. So Abel's formula states that your Wronskian at any general point is given by Wronskian at x naught exponential minus of a1 upon a naught dx. And on any time, you know that for in any way, your exponential function is always a positive function. So don't worry about it. Now, if you happen to know that your Wronskian x naught is equal to 0, what does it imply? It implies 0 into positive is 0. It implies Wronskian x is 0 for all x belongs to it. Okay, so if at one point you know that your Wronskian is 0, then Wronskian is 0 for all x belongs to it. Is that clear? And if at a single point you know that your Wronskian is non-zero, now there may be two cases. It may be either positive or either negative. So if it is positive, then Wronskian will be positive throughout. And if at a known point you know that your Wronskian is negative, then Wronskian will be negative throughout. But it will never be zero. So it cannot be simultaneously zero as well as non-zero on single interval I. So either it has to be completely zero, either it has to be completely non-zero. Now, what is the benefit of it? So coming next to that, you see that if your property number third, if y1 and y2 are linearly dependent, okay, if y1 and y2 are linearly dependent, what does it imply? It implies I can write my y1 as k y2, and I can write y1 upon y2 as some k, and let us differentiate it. And I'll find that y1, y2 dash minus y2, y1 dash is equal to 0, divided by y2 per square, obviously. Okay, take that there. So you can write this is nothing but this is equivalent to writing Wronskian equal to 0. So if I take that y1 and y2 linearly dependent, it implies Wronskian is 0. And if I take these conditions that if Wronskian is 0, I can arrive at these conditions. So always understand that if Wronskian of y1 and y2 is identically 0, is identically 0 if and only if. If and only if means both ways. Like if you take that solutions are linearly dependent, then Wronskian will be 0. And if you get your Wronskian is 0, then I can write that my solutions y1 and y2 are linearly dependent. If and only if y1 and y2 are linearly dependent. Independent, dependent, sorry. Are you getting my point? Fourth property is that if I'll write same here, but now I'll write for linearly dependent. Wronskian of y1 and y2 is never 0 if y1 and y2 are linearly independent. Or rather, you can say y1 and y2 are linearly independent. It implies Wronskian would be non-zero. So you can write that both of these things are true. That is, I can write that my Wronskian x is non-zero, implies y1 and y2 are linearly independent, and y1 and y2 are linearly independent implies Wronskian is non-zero. Is that clear? Okay. Also, you can write that if I know that my solutions y1 and y2 are linearly dependent, then there would obviously exist some x naught belongs to I such that Wronskian at that particular point has to be 0. कोई ना कोई point 0 मिलेगा जहाँ Wronskian 0 हो जाएगा. Because at one point if Wronskian is 0, then it is entirely 0 for the entire interval of existence. Is that clear? And sixth point, if y1 and y2 are linearly independent, then there exists some x naught belongs to I such that Wronskian x naught is non-zero. I hope till now everything is clear. Or are there any questions? Are there any questions? Kindly let me know. कोई कुछ तो बोलो, कहाँ गए सारे?
No, sir.
ओके, अल्पना, भरत, कृति, मोनिका, रजित और कौन है भाई लास्ट? सलोनी. I hope it is clear. So this Wronskian theory is quite important, and I've already told you that these are just basic mathematics lecture that I'm teaching you. I will teach all these things in more association to physics later on. But right now, I want you people to at least have an understanding of, like you can say, an overview of things, so that you're able to. So the biggest example, the best example for studying these second order linear differential equations or second order homogeneous or non-homogeneous linear differential equation can be to study damped harmonic oscillations and forced harmonic oscillations. Okay, and the entire theory you will find that is somehow applicable there. Okay, somehow means it's entirely, if you really see that what are oscillations, they are nothing but solutions for a differential equation. Okay, so eventually you can associate all these things there. So I'll do a few more lectures more on physics side, so that we'll do later on. But first try to understand that how to find the solutions, how to think over them. So I'm right now more concerned with the mathematical reasoning part. Is that clear? So a few more things, if you really can bear them up, I can teach. And if you cannot bear them, I'll leave that. But let us first do a few questions so that you get some sort of inspiration that whether or not uh, this is important or somehow. Okay. So let us do a question from net examination. And it was asked in December 2012. Okay, so let us do this question. This was asked in net December 2012, and it says that x1 as a function of t and x2 as a function of t are linearly independent solutions of differential equation given by d2x upon dt square plus 2 dx by dt plus f as a function of tx equals to 0. And it defines, let wt be defined by x1 as a function of t dx2 upon dt minus x2 as a function of t dx1 as a function of t divided and dt, and says that if w0 is equals to 1, then w1 will be equals to what? So this was asked in net December 2012. Let us try to solve this question. I'm not giving the option. We just need to find what is w. So how to go about it? So clearly you can see that this is a second order homogeneous linear differential equation. And this pattern, that is x1, x2 dash minus x2, x1 dash, suggests that this is nothing but given, what is this? This is nothing but this is Wronskian determinant. And I have already stated that if even at a single point, if you know that your Wronskian is non-zero, then it will be completely non-zero. Rather, it was initially supplied to you that x1 and x2 are linearly independent solution. What does it imply? It says that your x1 and x2, the Wronskian can never be zero. So obviously you can see that at a single point you've got a non-zero value. So overall it will be a non-zero value. Okay. Okay. How to go about it? So I've told you what is Abel's formula. Abel's formula says that if I want to know what is my Wronskian at some point, and if I know what is my Wronskian at some my known point, so it is equals to this minus integration 0 to 1. A1, instead of A1, you can write 1. Instead of A0, you can write as, sorry, instead of A1, you can write 2. And instead of A0, you can write as 1. So this is how it is. You integrate these things and you'll get an answer to this. So Wronskian at 1 would be equals to Wronskian at 0 is 1 into e to power minus this 2, it will become 2x, 0 to 1 is 2. So this will be like, so Wronskian at 1 is given by 1 upon e square. Is that clear? So it is a 2, like, these are very easy questions. Are you getting my point? Or not getting anything? Are you getting my point or not getting?
Yes, sir.
Okay. So I hope it is easy. It was an easier one. Let us raise our levels and try to do a few more properties. So few more properties. I hope these are slightly difficult, but I'm just attempting it. However, for physics people, this will do. Like till this, everything is done. Yeah, I mean, when it comes to examination, otherwise also, if you know this much of theory regarding Wronskian, you will be all done for your exam. Okay, but let us try to see a few more things in detail, and I'll do it very shortly. And even if you don't understand them, try to remember them as properties. Okay, so I'm just I'm just stating. So this is your Wronskian determinant, and I'm writing it for second order linear differential equations only right now. I'll write it for nth order linear differential equations as I can write it for nth order linear differential equations as well. So what is y1, y2, y1, y2, y1, y2, y1 dash, y2 dash? This is Wronskian determinant for the two solutions y1 and y2, which happen to be the solutions of a second order linear differential equations. Okay. Now, suggest me ways in which I can make this Wronskian as zero. Okay. So one of the ways can be to make this entire row as zero. Okay. So if and understand these all are functions of some x. Okay. So they have to be evaluated at same point, right? Is that clear? So if I say if y1 and y2 simultaneously become zero at some x equal to x naught, then what will happen? Then it will happen that Wronskian will be zero, isn't it? So if this simultaneously becomes zero, then the entire Wronskian would be zero, isn't it? Yes or no? Yes or no? And if Wronskian is zero, that implies my y1 and y2 are linearly dependent. Is that clear?
Yes, sir.
Okay. And if my y1 and y2 are linearly dependent, so what I have come to a conclusion that if y1 and y2 have common roots, or common zeros, what does it imply? It implies that y1 and y2 are linearly dependent. Okay. Is that clear? What assertion I can make that if y1 and y2 are linearly independent solutions, then it implies Wronskian can never be. If y1 and y2 are linearly independent solutions, then y1 and y2 can never have common roots. Because if they have common roots or common zeros, then this entire thing would become zero at some point x naught. And if they become at some point x naught, they become zero, then Wronskian at some point would be zero, then Wronskian would be zero throughout. So understand my point that if y1 and y2 have common zero, then y1 and y2 have to be linearly dependent. Rather, I would say that if y1 and y2 are linearly independent solutions, then y1 and y2 cannot have common zeros. Is that clear? Another way of making it zero can be to say that if this column becomes zero. So if this column becomes zero, then also or this row becomes zero. So I'll stick to this last point. If the lowermost row becomes zero, it implies what? There exists some x naught belongs to interval of existence I such that y dash x naught and y2 dash x naught are simultaneously zero. It means if y1 and y2 are having common points of extrema, it can be minimum as well as maximum. Common points of extremum, it implies y1 and y2 are linearly dependent. See, if this is zero, it implies y dash x naught is zero, y2 dash x naught is zero. That implies y1 and y2 are having common points of extremum. And if they are having common points of extremum, this row would become zero and overall Wronskian would become zero. And Wronskian, if at one known point is zero, then it is zero throughout. Otherwise, I can write y1 and y2, if they are linearly independent, it implies they cannot have common point of extremum. Is that clear to you? Is that clear?
Yes, sir.
Okay. So we'll meet in the next session because the time is